deposit the P plus material onto the wafer, it reaches a P sub instead of the FOX. FOX is just insulator, doesn't do anything. You need the sub, you need the P sub to receive that P plus material. Let's go through this one more time. Okay, here's P sub. P-type substrate, or P sub. A lot of times we call it body. Okay, P sub is a substrate. It's basically just a wafer. There's a wafer holding all these kind of semi-integrated circuits. It's a wafer itself. If I draw this, I label this as P act or P active in electric VLSI. This layer is a mask that is able to open up FOX on the P sub. Originally, you have homogeneous FOX on the top of the P sub, but this guy is going to open it up. So eventually, there will be an opening of FOX. What FOX means? Filled oxide. It opens up FOX, then you remove the mask. You place the wafer inside the environment, vacuum, okay, high pressure, high temperature, whatever. Deposit that P plus material or N plus, doesn't matter depending on your application, right? It's a dopant. It could be N-type or P-type particles into it. So that kind of thing in the environment will diffuse into this wafer, and it's going to form a node. It could be P plus or N plus. But usually, if you only have a P sub, usually it doesn't matter. Can be a P plus. So P plus is like iPhone something plus, right? You know that it's just highly concentrated. It's higher concentration of the P-type material. The P sub is lightly doped by the P-type material, but the P plus is highly concentrated for some conductivity purposes. Okay, so it's P plus, and then you need a bigger box around it. This is called P select. Why? Because the P select is a window to deposit that P plus material into that opening. But the thing is, there will be a misalignment issue, so that's why you make this box bigger. So I have a bigger window, even though there will be some material deposit to the FOX layer, but it doesn't matter. Nobody cares. It's just an insulator. But eventually, just want to guarantee that all this opening has a P plus material diffused into it. Okay, that's a goal. Is that clear for this purpose? For this, kind of technology? Okay, let's move to the next. Come back to this figure. Look at it, and you see a P select, right? P select is definitely a bigger box. And you can see here is a shadow here. This one, right? This one. What is it? So the gray color, the gray box here. P act, right? How do you know it's a P act, not N act? Because it's P select, right? Okay. So what is this one? This box. This box. That's a metal, okay? That's metal 1. How did I know it's metal 1, not metal 2? Remember, this is the bottom-up technology. So right after the FOX is what? Poly. Right after the poly is what? Metal 1. Okay, you want to make a contact to the P plus. You drill a hole here. It's called a via. And you put a little metal 1 on the top. Now you're asking, how did you know this is metal 1, not poly? Because poly is over here, not here. They're in different layers. So the poly layer is the insulator. So this whole thickness is the insulator's thickness. And if you want to put a poly layer in it, you just have a poly layer in it, in the middle. Okay, that's going to be a poly material in the middle. That's what you can fabricate into that insulator layer, right? It's like the chocolate filling of the cookies. It's in the middle. Okay, so for this insulator, you have this metal inside the insulator layer. That's metal 1. So the metal has a direct contact to the P plus, the diffusions, has to be metal 1. If you want to connect this P plus to metal 2, you just have you need two vias. But apparently there's no other vias, just simply one via. So in that case, all these little squares, the black squares, are vias. All right, I'm gonna give you 2 minutes to draw the cross-sectional view of this guy, starting from this one. So the dashed line, I'm gonna just directly tell you this is unwell. So if I put unwell in this figure, put unwell in this figure, like this, for example, this is unwell. Yeah, we'll talk about why we need unwell later, but now just draw the layers. Okay, if this is unwell, then the unwell is gonna be here, and you label it as unwell. Okay, it could be underneath that fox. Doesn't need an opening to do the unwell thing because unwell is being put into the wafer at the very beginning, I believe. Otherwise, the fox will be removed. So it allows fox on the top of unwell, which is fine. So if you have unwell around it, it looks like this. So I'm gonna give you 1 minute to draw this cross-sectional view just for practice, and I'm gonna draw that later after 1 minute. Okay, so you can find out if there's any issues you have. So I'll show this figure for you guys as well, just in case. Remember, it's bottom up, starting from the bottom layer, and draw one layer by layer to the top. Start with a P sub. Okay. Start with the P sub, okay, because it's a bottom up technology. Just do this. It's a P sub. Do you need to draw anything for the P select? Oh, unwell first, right? Unwell. Probably running out of space, but let's see. And so that's the unwell. Then P select. Do we need to draw anything for P select or no? No, it's just a bigger box to avoid misalignment. So now this one is a P act. So putting a P plus material into it. Okay. So P plus is a P act area, so it opens up the flux. So we need to draw flux over here. It should be flux. And then what? Poly. Do we have poly? Nope. So keep it empty. Nothing. Do we have metal 1? Yep. Where's metal 1? Here. The whole bar is the metal 1. Okay? Metal 1 should be here. Do we have vias? Yep. Via 1, 2, 3, 4, 5, 6, 7, 8, 9. So many. It's going to take me forever to draw everything. The same, okay? Until here. Little vias. Little squares are vias. And above the via is what? Metal 1. Okay, metal 1. Is metal 1 one bar or separate little bars? It's just one metal bar, right? Just one metal wire. It's gonna be like this. Okay. It's metal 1. Okay, and then label it. So I'm 1. This is via 1. I think that's it. Okay, to receive full credit for the quiz. That's everything you need to draw. Okay. If you think you are so good at it, just draw metal 2, metal 3, can make it perfect. Okay, this is metal 2, but we don't have metal 2 layers. But these are all the layers exist. It doesn't mean that you don't have metal 2 and metal 3 in these layers and these won't be deposited onto the wafer. No, they are still there, but just doesn't have anything in that layer. Okay. Let's look at this one. Or this one. This is a transistor. We haven't covered much about transistors yet, but let's take a look at it. Keep in mind that this is a poly, and it's a gate. So there's nothing under the gate. It's a channel. So when you have the question regarding the technology dimensions, so like 5 nanometer technology, 20 nanometer technology. So this little thing is a length. Is a length of the transistor, which defines the technology. So the minimum length you can fabricate in that technology. If it's 5 nanometer technology, means the length here will be 5 as a minimum. That's a dimension. It looks like this is the width, this is length, right? That's wrong. Because you have these two terminals, the drain and source, the current flows that way. So that is why here's the length, because that's the direction the electrons travels. That's why it's the length. Okay, it's the distance of the electron to travel through. So here's the length. That's the width. Okay. Now let's draw the layers. Start with the P sub. So the question is where to draw. Like, for example, I draw a wire here, draw a line here, okay? The cross section of that line. Where to get started? First, the N well. You got N well. Let's draw the N well bigger so we have space for other things later. So N well. The dashed line, the box, is N well, keep in mind. So the N well is the bottom of the PMOS. We'll talk about this later, okay? Important to know. And that's why whenever you are transferring to using a different technology from TSMC, it's always the same concept. You need it's called N-type or P-type. These are well taps, well contacts. Just all the same concept. If you know one technology, you will be able to know all the others. Super similar. N-well, what's next? So this solid line of box is P-select. So we don't need to draw anything about that because it's just a bigger box to avoid misalignment, right? So what we need to draw is the P-act. So here's a P-act. That's a P-act, right? P-act. Keep in mind, I told you, channel, there's nothing underneath the gate. So we got a P plus here, and the P plus here, but in the middle is a channel. Okay, you shouldn't draw any P plus, otherwise it's shorting. P plus. Whenever you have a gate, keep in mind, whenever you have a gate or poly on the top, there's nothing underneath it. It's basically just a P stub or unwell. So you got a 2P plus. What else? So this must be Fox, right? These are all Fox. No issue on that. What is this layer? Polysilicon, right? The gate. Do I have a gate? Yep. Where's the gate? Here. That's poly 1. Poly 1. It's in the middle. So here's a gate oxide. GOX. What is that used for? That is why CMOS is more popular than BJTs, because it's not directly injecting current into the transistor. It's just creating an electric field to attract electrons or holes into the channel and then run the current through it. It's low power design. That's why CMOS takes the whole market after maybe 50 years ago. You know, BJT is not used anymore, unless in some of the power electronics. But for all the integrated circuits are all CMOS. Keep in mind, all CMOS. There's no direct current connection. It's just using an electric field. So the gate is a switch. Whenever you turn on the gate, it creates an electric field and attract electrons into the channel. We'll talk about this later today. Okay, no worries. So poly, you have one layer. Do you have metal one or no? Yep, you got metal one. The metal one is creating contacts to the P pluses, and they are providing terminals to the drain source of the transistor. So metal one has a width of this, right? Let me draw a dashed line just in case. That's the width of the metal one. So no, there will be a metal one here. Metal one. Sorry, that's a via first. So the black square, that's a black square. This guy. It's a via, and then you have a metal one on the top. A little bit wider than that via. You can see this box is a little bit wider than this little box, little square. So this is the via one, and this is metal one. Same to this one. Draw a via here, and draw a metal one here. Anything else? Anything else for this top view? That's the whole cross-section view of the transistor. That's it. You cut it in the middle. That's what you are going to see on the wafer. Okay. Any question on this?
How about the metal on top of the gate?
On top of the gate. There's no. Oh, you mean here? Here. Yeah, we didn't draw the line across it, but we can do it.
We just do another metal.
This one, this is metal one on poly. Which really good question. Let's draw it. Really good question. But any question on this by far? What's that?
So there's a poly layer above the Fox?
Yes.
Yeah?
Yes. Because there's a first layer of the insulator. That's
Is that a different polysilicon that is in the center?
You mean this guy?
Yeah.
That's a GOX. It's a gate oxide.
Then what's poly 1?
Poly 1 is this guy. That's poly 1. which is this width here.
Yeah.
Yeah. And that's the oxide layer.
But the whole layer is called poly.
Yes.
How are they different? Maybe let's make sure.
Or the whole layer. This layer, this little, so this layer here, right, is called poly, and this thing here is silicon dioxide. It's an insulator, which hosts that poly layer inside,
Yeah, okay.
and the gate oxide is another oxide inside that oxide layer, the first oxide layer, but at the very bottom of it.
Yeah, is poly 1 just silicon dioxide as well?
No, polysilicon. I don't know the detail of the material, but it's polysilicon something. I don't know.
Okay.
It's definitely very different because it's conductive. Yeah, silicon dioxide is not conductive because it's insulator, right? Should be totally not conductive. But the polysilicon is conductive to some extent. That's why we are using that material as a gate. You know, it's a gate. It's conducting voltages, but it has a higher resistance compared to metal. So that's why last time we were talking about, hey, if you want to use the poly layer over here as traces for your circuits, what you want to do? You have to deposit another metal layer on the top. So it's called silicide, right? Last time what I said, it's like this. Poly, for example, you deposit another layer on top of the poly, and this is called silicide. Metal, okay, it's the metal. To reduce resistance of poly. So here's a poly layer, for example. Doable. So when you guys are doing the layout, you'll see this a lot. You know why? Because a lot of times you feel like it's so easy to directly extend the gate wire, right? I can directly use the poly layer as a wire, and I can connect to all the other circuits, because it takes time and requires some space to drill a hole to the top and connect to metal 1, then route it. So you want to be lazy, you just want to directly use poly, but eventually you'll find issues. Let me give you one example here. Let's look at some of the layout examples. Let's look at this. Let's look at one. A little bit more integrated ones. Okay, like this guy, all right? So the pink color is poly as a gate, all right? This one is fine, but let's see if, for example, this guy, all right? And you see the gate, the poly layer, the pink one comes out. I can directly use, if I'm lazy, I can directly just use a poly and make the connections to all the places. You can see even from here to here, the two gates are shorted together. I don't even want to use just pure poly. See what I'm doing here? I got a poly out from the metal, all the metal wires, in between the metal wires, because there's no way that I can drill a hole on top of it. It's going to short the circuit to the metal one, which is a light blue color. So I have to extend it to on the right hand side wherever I have more space. So next to this metal one, and then I can drill a hole. It's a via. I drill a hole to the top and then connect the metal one to here, and then I drill it back down to poly and connect to this gate. Why do I have to do that? I just use poly. Why do I have to drill a hole to the top and then make the connections? To reduce the resistance. You just cannot directly use poly as a trace, as a wire. It has high resistance, right? If you use it as a wire all over the places, it's dropping voltages. Resistance dropping voltages. Because of the Ohm's law, right? You get current running through the resistor, it drops some sort of resistance voltage, which is bad. So even for this very short distance, I believe it's just a few hundred nanometers. I still don't want to just use poly. I convert it to metal first and then come back down to the poly layer. This happens in so many different places. You can see the examples like this. You can see from here is the gate, right? So the circuit design requires this pink layer to be shorted to this place for some reason. I don't know, but you know. And you see that right after this poly layer get out of the transistors dense area over here, whenever I have a space, which is not against the design rules. For example, it has a required spacing. Okay, I directly drill a hole to metal 1 and connect to metal 1. Okay, and then I have to connect to the yellow color, which is metal 3, because I know there are metal 3, metal 1 in here. Okay, so I have to cross these two metals in order to make the connection to here. So in that case, I have to drill a hole to metal 2. That's why last time someone was asking, why do we need 3 metal layers? That is why, right? Sometimes you have metal 1, metal 3 horizontally, and you want to cross it. You just have to route it through a different metal layer in order to not shorting it to the other traces. Okay, so the purple color is going to be metal what? 2. Because yellow is metal 3, blue is metal 1, purple is metal 2. That's all the 3 metal layers we have for C5. Okay, another question. Since I need a metal 2, why not just directly use metal 2 here? Why do I still need a metal 1?
In order to go up a layer.
Huh?
In order to get through.
Yeah, one layer at a time, right? There's no via called via 1, 2. Via 1 shorts it to metal 1, via 2 shorts it to metal 2. There's nothing like can drill a hole throughout the whole chip, right? It doesn't exist. So drill a hole first and to metal 1, drill another hole to metal 2. That's how that works. You can imagine the shape in the 3D structure in your mind. Okay? Make sense? Let's draw the layer for this guy here. If I draw a wire here, what's going to happen if I draw a wire here? Think about it. Take 1 minute. Take 1 minute to draw it. What is this guy? Poly. What is this guy? Metal 1. What is this guy? Via. It's the first time we draw a metal 1 to poly. See how that works. Take 1 minute to do it. You can. Piece out first. Do you have diffusions or no? Do you have any P plus or N plus? You have it here, but not here. Okay, so do you have Fox? Yes, there's no PX to open up the Fox. So there will be a Fox over here. Do you have poly? Yes. This is poly. There will be a poly layer. Do you have metal 1? Yes. Boom, boom. Via metal 1. Okay, that's it. Oh, that is wrong. Why? A minor issue.
Well, like, don't you have the poly like on the 2 sides like this?
Uh-huh.
And
So
it's I don't know. I guess I'm like confused with like how do you like separate the vias and the polys?
Yeah, so very close, Sarah. What you want to say, really? Yeah.
Like it's like it kind of looks like two different poly like on the side and then like in between.
Oh yeah, it's actually a bigger poly underneath it. So the thing is, why is it slightly wrong? Because poly is wider than metal, right? But you see what I'm doing here? Metal is wider than poly. Minor issue, 0.5 points off. Right? Poly is wider. Right? Poly is wider, see? Poly is wider than metal.
Would there be more metal on either side?
Guys are so smart. Okay. Any question on this before we moving forward?
I'm so confused how you know that's a poly layer. Is it just because it's dark? Or?
Because on the top of the diffusion, it's a gate. So here's a transistor. It's a diffusion. So that's why you have a. You see, this is really common structure in the design. If you go through all the labs, you will be able to tell. See, this guy, that's a transistor. This is two terminals, and here's the gate, and underneath it is the channel. We haven't covered CMOS transistor yet, but just let you guys know the structure right for now.
So which color is poly there?
Pink, which is your favorite? My daughter's favorite colors. Everything has to be pink. Yeah. So what are the dots? Dots are N-wells. So PMOSes has to be fabricated in N-wells. So the N-wells are the substrate for the PMOS. Just to let you know, we'll cover more about this later. So N-well is the body of the PMOS, and the P sub is the body of the N-MOS. So the dashed lines is not a specific well. It indicates a universal P sub. It's just trying to differentiate from N-well. So P sub will be the dashed lines. All the N-MOSes are fabricated in P subs. And all the PMOSes are fabricated in N-wells. So the dotted field is the N-well. And the N-well, you need a P plus to be put in N-wells in order to not shorting P plus to P sub, because P subs are usually shorted to ground. So P plus, if P plus is shorted to ground, then you have the transistors, two terminals are shorted to grounds. At the same time, there's nothing can run through the channel. We'll talk about this later, doesn't matter. Just, a lot of things to cover. Yeah, what's that?
So polysilicon is the layer that you put between the source and gate, and it's not metal.
No.
Okay.
It's probably 200 ohms per something micron, I think. It's conductive, but not a metal, but not as conductive as metal.
Okay. And
Yes.
and that first example that you did,
Yeah.
I did that one on the top. Yeah. That in that layer we don't have a poly because you don't have the
It's not a transistor, it's just a
Yeah.
something, yeah, like a
Okay.
wire.
So as long as you don't have a transistor, then you don't have the polysilicon at all.
You don't need it, that's right. So the polysilicon is used as a gate and also used as a cap. So we are forming capacitors using polys as well, but now it's seems like none of the cases here, right? It's just a diffusion.
And all wherever you have the vias and the metal layer, it's like around it is always sodium dioxide.
Yes, like this. Yeah.
Okay.
What happens to the metal that doesn't have vias? Are they just like sitting on top?
Yeah, there must be vias somewhere, right? Even though it doesn't have vias. if I draw a wire here, okay? So these metal ones don't have a via, but they must have via somewhere else in order to be meaningful. If it's just an insulated metal in the middle of the layer, why do we have to use it? Right? It's gonna be like an island. What's that?
Is there always a gate oxide under?
Poly?
Yeah.
Good question, actually. If you are not using that as a gate, do you still need that gate oxide or no? I don't know.
Like there will still be an oxide layer though under the polysilicon.
If you're not using that one as a gate, probably not. If you're just using poly and another layer of poly to form a capacitor, P sub, right? Fox, poly, and you have two poly layers here actually. Poly 1 and poly 2. You can drill vias to metal 1. To form a cap.
So if the gate oxide doesn't come directly from the polysilicon,
Yes, I believe you don't have a gate oxide if it's not a gate.
where does it come from?
Where does it come from? It comes from a fabrication process. I think if they know it's a gate, if they know the gate, they will probably do a layer over there underneath the poly.
But it's in the polysilicon layer.
Yes, it's in the layer, yes. Yeah. It's right above the P sub actually. Whenever the Fox is getting removed, it's right above it. It's very thin in order to form a strong electric field. So it's really, really tiny layer over there, very thin.
Is it above the Fox?
Above the P sub.
But
Oh, the Fox is gone. If you have a transistor, the Fox is gone because you have this P active. The Fox is gone, right? It opened up,
okay.
has nothing on the top anymore. So it's gonna be something like this. Fox is gone, and there will be a, for example, this is a P plus. That's a transistor, and there's the gate oxide in between the poly and the direct to the P sub.
Yeah. So there won't be gate oxide and Fox at the same point.
No.
Okay.
So you can imagine, so, we haven't covered that yet, but let's just talk about this briefly. So for a PMOS, right, we usually connect a source over here to create a voltage drop. It's going to be, it's called VSG. This is gate, this is source, for example. It's VSG. So VSG has to be higher than a certain threshold voltage in order to turn on the channel. So how the channel is being turned on? It's actually because you compare to the P plus, definitely in the unwell here, anyway. So the gate has a relatively lower voltage compared to the source. So basically this is a cathode connect to the gate, and eventually what's happening is in the unwell there are holes and electrons. So the holes will be, the holes will be attracted to the channel and to form a layer of holes. Okay, so the holes are aligned in the channel and ready to be driven by the electric field. So if you ground this guy, and here you provide another power voltage source. Okay, so what's going to happen is this positive terminal of the battery is going to expel all these holes because plus and plus is going to drive it to the left. So it's going to form a current flow in the transistor. So that's how that works. You have to apply a voltage source here first to attract the holes in it. Okay, so the holes are ready, aligned in the channel, and they're ready. Okay, and then you apply a voltage from source to drain. It's called drain. Source to drain. Okay, and then you drive that, provide electric field horizontally to drive these holes to the left to form a current flow. So I have to turn on the gate first. That's why it's called gate, right? It's a switch. You turn on the gate and then apply a voltage to drive the holes. Actually, not driving the holes are not moving, right? It's actually electrons moving the other direction. Okay, but basically it seems like the holes are moving to the left. Anyways, the holes are the positively charged, right, particles, and when these ones are flown to the left, the current flows to the left. Okay, but basically, physically, what's really happening is the electrons move to the right. But we don't care. Electrical engineers, we don't care about electrons. We don't care about currents, right? Currents flow to the left, then current flows to the left. We only care about what's being read on the multimeter, right? We detect current. Yay, happy. Who care about the electrons? Do whatever you want, okay? You know what I mean? So everything flows to the left to form current. So one interesting thing is, you can see whenever that's why it's called length. Length, okay, that's the length of the transistor. So whenever the length shrinks to like 5 nanometer, I think under 20 nanometer, it's not a CMOS like this anymore. Anything under 20 becomes FinFET. The reason for that is it's too short. So the poly on the top with the gate oxide on the top, because it's too short, you can imagine it's not able to have provide a large enough aerial footprint to provide that voltage on the top of the channel to offer that electric field to attract holes to the channel. You know, the aspect ratio is too small from the length of the gate versus the channel's area. So in that case, there's new technology called FinFET getting developed. So you cannot just directly place something on the top to provide electric field. You have to wrap it. You know what I mean? So for example, if the stack of paper like this was a channel, okay? Was a channel. So here's a channel. I can have a little gate on the top to provide the electric field to run current through the paper, okay? So we'll never have 5 nanometer technology like this. So the paper thickness is the length of the channel. And you place something on the top, it's really difficult to provide electric field into that channel in order to have enough holes to run through the channel. So what's going to happen is there's a new technology called FinFET. It's not really new anymore. I mean, it's like 8 years old technology already. Anything below 20 nanometers, okay? It provides the technology called FinFET. It's like a fin, right? And then the gate is not just one dimension anymore. It's a 3D. It's wrapping around, okay, around that channel. So it's providing enough electric field around the channel in order to attract enough holes in the channel. So it's wrapping around it, called FinFET. So about 6 to 8 years ago, this was firstly introduced in the industry. I think Samsung was the leader in this technology, but right after like 1 year or 2 years, TSMC just take over everything. So all the 5 nanometer technologies, all of them has to be in FinFET. Okay, it's impossible to have a gate on the top to control everything. It's not controlling the switch anymore. So I have to wrap it. We got like 10 minutes. Let's do the quiz.
Have they gone over enough in class to become more by Friday, or is it maybe get questions?
I'll take that out. We're a little bit slow this today. Interesting. Got more copies? No? I'll take it. Maybe you can take a picture of this one first. Oh yeah, I do have one more copy here for some reason. Just have such a good attendance today.